Welcome back to The Explainer. So think about this. We spend our entire day browsing the web, right? We completely trust our web browsers to protect our data, our accounts, and essentially our digital lives. But what if I told you that in certain situations, your very own browser could be manipulated into acting as an unwitting accomplice in a digital heist? Today, we're unmasking a really fascinating vulnerability from the world of web hacking. It's called cross-site request forgery, or CSRF for short.
Just imagine this scenario for a second. You log into your highly secure bank account. You do everything right, but simply by opening a new tab and clicking a seemingly harmless link, your trusted browser basically turns into a double agent. It flashes its saved credentials and authorizes a transfer of your money straight to an attacker. Now, this isn't some science fiction plot. It's the core reality of a CSRF attack. And to understand how an attacker actually pulls this off, we first have to understand exactly how websites remember who you are. The key to this entire vulnerability revolves around the concept of the cookie. You see, the underlying protocol of the web, HTTP, is entirely stateless. That means every single request you make is treated as a brand new interaction. Our source material actually compares it to having a conversation where before every single sentence you have to completely reintroduce yourself, kind of like the movie 50 First Dates. To fix this massive headache, websites use cookies. Once you log in, the site drops a small file right into your browser. From then on, your browser automatically presents this cookie, like an automatic VIP pass, with every single click, so you don't have to keep logging in over and over. It's incredibly convenient, absolutely, but this automatic, reflex-like behavior is exactly what creates our vulnerability.
Let's break down how this actually plays out in a classic 5-step scenario. Step 1, our target, let's call him Bob, logs into his bank. His browser gets that VIP pass cookie. Step 2, without logging out, Bob checks his email in another tab. Step 3, he clicks on an unfamiliar, malicious link. Now Step 4 is where the magic happens. That malicious site secretly instructs Bob's browser to send a money transfer request back to his bank. And Step 5, well, because Bob's browser automatically includes his VIP cookie with that request, the bank just assumes Bob intentionally did it, and they process the transfer. Boom! Bob just got robbed, and he didn't even know it happened.
So how exactly does the malicious site pull off the dirty work behind the scenes? That brings us to Act 2, Anatomy of a Forgery.
When an attacker goes to work, they're usually leaning on one of two types of HTTP requests, GET or POST. Now, a GET request is supposed to just retrieve information, while a POST request is meant to submit or alter data. If a vulnerable site actually allows data to be altered via a simple GET request, the attacker has it easy. They can just use an invisible image tag. But if the site properly requires a POST request, the attacker has to work a little bit harder. Typically, they'll use a hidden HTML form that gets automatically submitted in the background by JavaScript the absolute second the victim loads that malicious page.
Consider a simple HTML image tag to really illustrate this GET request attack. To your browser, an image tag is just an instruction to load a picture on the page. But if an attacker sets the source URL to something else, like a specific web address designed to tell the bank to transfer $500 from Bob to Joe, things get messy. When the browser tries to fetch what it thinks is just an image, it sends a GET request to the bank and automatically attaches Bob's VIP cookie. The bank processes that URL, completely ignores the fact that it's not actually an image, and happily transfers the money.
Now, browsers aren't totally defenseless here. They have a built-in security guard called the Same Origin Policy, or SOP. The crucial point to remember is that while the browser will blindly send that malicious request to the bank, the SOP restricts the malicious site from actually reading the bank's response. The SOP is there specifically to protect innocent websites from malicious sites that are attempting to exploit the user. It basically ensures that documents from one origin can't just freely reach over and pull sensitive data from a totally different origin.
So what actually makes up an origin? Let's break it down. An origin is defined by three specific things: the protocol, the host, and the port. If we start with a standard HTTP example.com web address, adding a folder path to the end of it is totally fine. That's still the same origin. But if we change the protocol to HTTPS, blocked. If we change the host to a subdomain like store.example.com, blocked. If we add a specific port like 8080, again, blocked. All three of those elements must match perfectly for the browser to allow free interaction.
But here's the catch. Modern web apps actually need to share data across different domains all the time. Enter cross-origin resource sharing, or CORS. CORS acts as the secondary layer of defense. It defines strict rules for exactly when and how websites can read responses from each other.
For sensitive requests, like sending complex JSON data, the browser will first send a pre-flight check, called an options call, to the server. The server then replies with a whitelist of trusted external sites. If the malicious site isn't on that list, the browser steps in and stops the attack dead in its tracks.
All right, mechanics covered. Let's look at how this plays out in the real world with Act 3, Tales from the Field.
When you're out there bug hunting in the real world, you really have to flip your mindset and think exactly like the attacker. You have to constantly poke and prod at the boundaries of how these applications handle trust and authentication. You have to be asking yourself, where is this developer trusting my browser just a little too much?
Our first case study comes from Shopify. A bug hunter noticed a specific URL that was designed to disconnect a user's Twitter account. The massive problem here? Shopify was allowing this disconnect action to happen via a simple GET request, completely without verifying where the request actually came from. The hacker proved they could simply embed this exact URL into an invisible image tag on a malicious site. If a logged-in Shopify user visited that site, their browser would try to load the image, hit that URL in the background, and instantly sever the user's Twitter connection. It's a perfect, textbook example of a GET-based CSRF attack.
Now, our second case is a bit more complex, involving the social network Badoo. Badoo actually had CSRF protections in place. They used a unique token called the RT parameter. However, a clever hacker named Mahmoud Jamal noticed something really odd. Badoo's tokens were only 5 digits long. And worse, he found the token actively leaking in a publicly accessible Badoo JavaScript file. Jamal crafted an attack page that loaded Badoo's JavaScript, used his own custom script to extract that leaked 5-digit token, and then automatically appended it to an account-linking URL. He then forced the browser to redirect to this new URL. Because he hijacked a totally valid token, Badoo accepted the request, which allowed him to link his own Google account to the victim's Badoo account. This resulted in a complete, full account takeover.
And the best part? Because Jamal ethically reported this through HackerOne, Badoo patched up the critical vulnerability long before bad actors could exploit it. For his ingenuity and persistence, Badoo rewarded him with a bug bounty payout of $852. A really great win for the good guys.
So how do developers actually stop these digital double agents? Let's get into Act 4, Locking the Vault.
The most robust defense out there is exactly what Badoo is trying to implement, this CSRF token. Think of this like a secret handshake. When you log in, the server gives your browser a unique, complex, and totally unguessable token. Whenever you submit a post request to change any data, you have to include this token. Because of the same origin policy and cores that we talked about earlier, an attacker's malicious site cannot simply read this token from your browser. So when they try to forge a request in the background, they don't know the secret handshake, and the server just flat out rejects it.
Another incredibly powerful modern defense is the SameSite cookie attribute. Developers can essentially tag a cookie as either strict or lax. If a cookie is set to strict, the browser will absolutely never send it if the request originates from an external site. For example, if you click an Amazon link from a random blog, you'll arrive at Amazon logged out. If it's set to lax, the browser will send the cookie, but only on initial GET requests, like naturally following a link, which shouldn't be altering any data anyway. This is a massive, highly actionable takeaway for developers to immediately shut down CSRF attack vectors.
Which brings us to our final thought for today's explainer. As we've seen, relying solely on cookies means you are placing completely blind faith in a piece of software that can easily be manipulated by malicious code. So the next time you build an application, or really even just log into one, ask yourself, is this website actually verifying the intent of the human user, or is it just blindly trusting the VIP pass held by their browser? Thank you so much for joining me on this explainer. Keep your digital vaults locked, and I'll see you next time.